In this video, we're going to talk about reaction rates and the effect of temperature on rates. So if you look here, you've got a reaction here in a set volume, and you have got an increase or a decrease in temperature. Now, if it's an increase in temperature, your kinetic energy will go up and your particles will become faster. And that's our top keyword. And they'll collide more force. Okay. And again, those two words are not really used in mark schemes that much, but it's good to put them on just in case. And then obviously if they're going faster and they're going with more force, they're going to more frequently collide, and they're going to achieve the necessary activation energy, and the rate will go up. Okay, so we use all our key words, but let's show you this practically. So we have got the two particles coming at each other quite slowly. Notice they hit each other not very fast and they don't really react. Okay, but we're going to increase the temperature now and look what happens. Okay. So what happens is bang, right, okay, and then they come together, right, and they change straight away. So increasing kinetic energy means I'm going to get that energy for activation energy, and I'm going to get my reaction to occur. So if we take that away and we start thinking about what the actual answer is. So if I go here and I go, right, okay, what am I first going to get? Well, first of all, I'm going to get an increase. Okay, so a temperature increase. So a temperature increase increases, and think about what this word would be, increases kinetic energy. Okay, so it increases that kinetic energy, which means you'll have more force. So we've used our keyword. So I jump over here and get out from behind the writing. We've used this and we've used this. Okay. As well as that, you will get, and you can do it in bullet points if you want. Some subjects don't like bullet points, chemistry doesn't mind. Okay, you'll get more frequent collisions. Okay, so we've used our third one and our fourth one. So let's tick these off again as we use them. And I'm just trying to show you how using these keywords really works. Okay, so more frequent collisions, more successful collisions per second. You don't have to use it, you can just say frequent. Okay. And that means more collisions achieve, and I'll put it EA to shorten it. EA means activation energy. Okay. And the rate increases. Okay. So let's have a look at that now, shall we? If we do a temperature increase, you increase the kinetic energy, there's more force, okay? And that means in terms of collisions and more frequent collisions, and these are what's going to get you the marks, more frequent collisions and more collisions that achieve activation energy, EA, and the rate will increase. Opposite of that is temperature decreases kinetic energy, decreases the force of the collisions, means there's less frequent collisions, and less collisions achieve activation energy, and rate decreases. And that is how you structure a question using all of the keywords over there for changing temperature rate of reaction questions. So we're now going to go on to doing the Boltzmann distribution curve, which is also known as the Maxwell Boltzmann distribution curve. And it is the number of particles here on our y-axis with the kinetic energy of the particles down the bottom. We're going to plot it at T1, temperature 1, which we're going to say is around 300, but the temperature doesn't really matter that much. Now, if that's the case, we're going to plot several different things. So EA2 as in activation energy 2 and activation energy 1. Okay, so we've got activation energy 1, activation energy 2. Now, think about it. Which one's which? With a catalyst, not with a catalyst. So which one is with and which one is not? So this is without a catalyst because catalyst lowers the activation energy. So you can see it's lowered. This is with the catalyst. Now, we've got those two things, and now we're going to plot our data. So when we plot a Maxwell Boltzmann distribution curve, it always has a big hump like this at the start. And that's saying the majority of particles, okay, so remember this is number of particles, and the higher the line is, the higher the number of particles. So the majority of particles, okay, are at this lower kinetic energy. Okay, and the area underneath the curve is relative to the number of particles you have. Okay, and think of it as a set number of particles. Now if that's the case, it then goes down, then as I go across my graph, it then continues to go down just slowly. But it never reaches the end because in terms of physics and everything, theoretically, there can be particles with infinite amount of energy. It also starts from zero. So it's going from zero up. The reason I'm saying this is because you may have to draw this, or you may have to label this, or you may have to describe this. So it's really, really important. Now, if that is the case, we're going to plot another one, this one at 330. So we're going to increase the temperature. Now, if we're going to increase the temperature, majority of particles are going to have a higher energy than on this one. So it's 300, 330. So they're going to have a higher. So that means this hump is going to move slightly to the right. Okay? And as you can see, it's moved slightly to the right. So the average energy of a particle is somewhere around here, and then somewhere around here. Now, if that is the case, you can see that it goes down at a slower rate and then ends up having more particles with higher energy. And that makes sense because you've highered the temperature and you've highered the overall kinetic energy of all the particles. So it's gone up. And if we were going to go to a lower, it would do the opposite. So think about it. If you draw a line like this, the lower will have a peak around about here. So it will come up like this. And then if at a lower temperature, it will come behind here and then underneath. Okay? Now, I'm only going to draw two. And I'm going to start drawing it out for you here. So let's think about it first of all. Let's think about which ones have the necessary activation energy. So all the particles that give the area underneath here, so I'll just do this one right there. There you go. That is all the particles that will have the necessary activation energy. So necessary activation energy without a catalyst. Now, if we add a catalyst, you can see that all these will have the necessary activation energy. So therefore, the rate of reaction will go up with the catalyst. So what if we, instead of adding the catalyst, we take the catalyst back out and we increase the temperature? So we have all this extra particles. Remember that area underneath the curve is relative to the number of particles. So we've got all those extra particles that will also have the necessary activation energy. But then at the higher temperature, we add the catalyst. And you can see there's even more. Okay, so this is a kind of explanation as to why when you increase the temperature, why does the rate of reaction? Well, they've got necessary kinetic energy for the collisions to be successful, and therefore the activation energy achieved, and as you can see, the activation energy on those two parts. So now we've shown you the different parts of the Maxwell Boltzmann or Boltzmann distribution curve. Okay, it's now important to go through some little details if you're answering questions. First of all, the area underneath the curve is equal to the number of particles in the sample. That means on each of these curves, the area underneath them should be the same, okay, because the area is relative to the number of particles, okay, and this should look roughly similar. See, this has lost some space here, lost some area here, and then gained it down here, and this area should equal the loss there. No molecules with zero energy. So even though we start from here, there's no actual molecules with zero energy or particles with zero energy. No maximum energy, which means basically this never stops. Only those with an energy greater than EA are able to react. So once they're past this line here and this line here, if they've got a catalyst or not, they will react. So important things though, drawing it wise, if you have to draw it, is never let this line touch the x-axis. Okay, always start from here, okay? And if you're doing different temperatures, think about it as a line going like this. That's where your peak will be. So if I draw a line there, a lower temperature would have its peak up here, okay? And a lower temperature would come behind here and underneath, okay? Right, so that's how you draw a Maxwell Boltzmann distribution curve, and that is how you determine how many particles are available to or are going to react using the graph.